Hello and Assalamualaikum everyone. So we are from Group 1C or 1C are going to present our open-ended experiment which is experiment 14. So the topic of this experiment is the analyzing fluid flow and level control. So first of all, I will introduce ourselves. My name is Ahmad Kusai bin Alias and my metric number is 198956. And Abdul Wahab bin Abu Wahab 197900. Muhammad Ishaq bin Muhammad Azwardi 196199. Jiwan anak lelaki Witi Linggap 197188. So the objective of this experiment is to study the effect of parameter proportional, which is P, integral I, and derivative D, component value to the performance of level or flow control system. This is as known as PID. So the introduction is the model plan and process are now regulated to meet specific goal. Pressure measurement are taken in several areas in this scenario, such as tank storage, pump, compressor, furnaces reactor, heat exchanger, and so on, or from the connecting pipes to and from the equipment. For the equipment to work at its optimum, it needs a control system to prevent and limit sales error. And as a result, in the search of ideal parameter, a good trial and error strategy can be used with geometrical progression. Okay, that's all for me. I would like to pass to the next presenter.
Okay, thank you, Ai. So the apparatus for the experiment is the two machine and software. The first one is SM514 PC level of flow control. The second one is DAQ master software. So this is the procedure for the experiment. So first step we need to the machine and pump system are both turned on. The second, the computer's DAQ software was open and connect button was hit to make the pump is turned off. The third step is the software panel's left walk. We need to right click on the TK1 for level control, TK2 for flow control, and choose run all parameters. Scroll down, and the fourth step is the parameter to area in the right box of the program panel was scrolled down. Then for the level that need to run, the expected value was set. So the maximum range is 6. So changing then we need to change the P component. So the value was set to 0 to disable the integral and derivative action with the controller in manual mode. So B controller gain was set to a tiny but arbitrary number such as 5, and then to record the data the software run and load button were used. Then the pump to let the water into the tank was turned on. So the graph reaction was taken note. So the value and present value point change should be representative of the system's intended usage. So F, the P controller gain increased by a factor of 2 and alter the set point again to observe how it affect the control variable response. So the goal is to discover the P gain value that causes the response to become underdamped and oscillatory. So this is the highest level of controller gain. So after that we need to revert to the previous number of P gain after the ultimate controller gain has been obtained. Now the P gain value has been established and we can add another control action if necessary. So the sixth is we need to change in the I element. So by introducing changing the element we need to begin by introducing integrate action by randomly increasing the integrate time. For example, 5. Set there we need to reduce by a factor of 2, changing the set point after each setting. Continue doing so until the response of the controller variable becomes underdamped and oscillatory. So the prior value was returned by multiplying it by 2. Now that we begin the I gain. The value of I gain we can be determined. So after that we just gonna adjust the D action if necessary. Then the final step is the pause button in the program. We need to click to record the graph occur after the process of optimal tuning by trial and error. So the picture was saved as well as the Excel CSV file for future reference. So next I will pass to Ishad.
Okay, thank you, Abdullah. So I will proceed with the result and analysis. So as you can see in the table here, we conducted three different experiments with three different value of heating derivation time, which is we set the heating derivation time for 6, 12, and 18. So next, let's scroll down. Okay, so first is experiment number 1, which is the heating derivation time is set for 6 seconds. As you can see in the figure here, it shows the graph of temperature against the time when heating derivation time is 6. And this result is taken from the software. So based on figure 5.1, there was no changes in the temperature during the first 1 minute. After that, the temperature increased by 1 degree Celsius after 1 minute and 50 seconds. Then the temperature started to increase consistently by another 1 degree Celsius and finally reached to 6 degrees Celsius after 2 minutes and 30 seconds. Then it was able to increase to 7 degrees Celsius. However, the increase became unstable and it decreased to 6 degrees Celsius. The unstable condition remains until the end of the experiment. So next, scroll down. So next is experiment number 2, which is the heating derivation time is 12 seconds. So based on figure 5.2, there was no changes in the temperature during the first 1 minute. After that, between 30 seconds and 1 minute, the temperature increased by 1 degree Celsius. Then the temperature started to increase consistently by another 1 degree Celsius and finally reached 6 degrees Celsius after 1 minute. Then it was able to increase to 7 degrees Celsius. However, the increase became unstable and it decreased to 6 degrees Celsius. The unstable condition remains until the end of the experiment. So next. So the last one is experiment number 3, which is 18 seconds. So according to the figure, there was no changes also at the first. Then there is an increase in temperature by 1 degree Celsius continuously after 30 seconds. The temperature increase remains constant for several seconds. However, the temperature started to increase slowly by another 1 degree Celsius. And lastly, it increased to 6 degrees Celsius after 1 minute 30 seconds. Then, once it reached 6 degrees Celsius, it was able to increase up to 7 degrees Celsius. However, the increase became unstable and it decreased to 6 degrees Celsius. The unstable condition remains until the end of the experiment. So that's all for the result. So I will pass to Jivan for the discussion.
For the discussion, water is used to stimulate physical processes in liquid phase. PID controllers can control both level and flow. Single-loop PID controllers are insufficient when the system is subjected to fluctuating inflow and more precise level control is required. By using a secondary or slave loop, cascade controllers must be used to smooth out the fluctuating inflow. Based on the result obtained, uh, for the values of I and D were kept constant and the P values were set as manipulative variable. For the first experiment, the P value is 6. It took around 90 seconds to rise from its initial position and 30 seconds to stabilize at the setting point. The rising pattern is quite linear. For the second experiment, the P value was set to 12. It also took approximately 90 seconds to rise from its initial position and 30 seconds to stabilize at the setting point. The pattern was quite similar to the previous experiment where there were no fluctuation at any point. For the last experiment, the p-value was 18 and it took around 120 seconds for the point to rise before it reached the stabilized point. Unlike the first and second experiment, the last one took longer to reach stabilized point. For the conclusion, the effect parameters of proportional, which is p, integral I and derivative d, component value to the performance of the level of flow control system were comprehended. That's all from me.